Vera, I just saw a paper in the Annals of Mathematics, and there is a paper in 2012 where you are one of the co-authors. You are beating all the stereotypes about mathematics being a game that is played by the young. Tell us something about the subject area of this 2012 paper.
I was able to take part in such a project and to work with the people by Christian Borks and Jennifer Chase and Kati Westergombi, and last but not least Laci Lovas, who is the center. I really feel happy and lucky because of that.
So the subject is limits of graphs. Can you say just in a few words something about what kind of limits this is and where it is coming from?
The title of the book is Large Networks and Graph Limits, where the title indicates that the whole thing started, and of course now it is related to many things, but started with a study of large graphs. And now we all know that in graph theory, now this became, in some sense, a new, but really not quite new subject, but now it became more and more important. And partly because of the so-called real-life graphs, like the internet or the web, or large graphs in social sciences, in the brain and in the nerve system. And all these graphs, it's not only large, but one cannot know quite precisely the graph itself, partly because it is a growing one, and partly because you really don't know all the edges. And this indicates that the questions are necessarily different. What we have for finite graphs, for small graphs, we cannot ask most of the questions what is investigated or which was asked for finite graphs. First of all, it would be senseless to ask questions for properties, to investigate properties which depend only on a small number of edges. So you see the graphs, you see some global properties, and of course behind the global properties there are some local ones. But one has to ask at the very beginning quite different problems what for finite graphs. And now, which are these questions? And these are the questions we asked from really when we started to work on that problem. That when are two large graphs similar to each other? When do you say that these two graphs are close, if you have two large graphs, that these are close to each other? How the local and global properties are related? And again, last but not least, if you have a huge graph, how can you approximate it with small graphs or with simple graphs? So I mentioned maybe 4 questions. When we answer these questions, all these 4 or 5 problems we are looking for are very closely related. And then it turned out that it is related to many different parts of mathematics. Algebra, topology, analysis, and so on is involved in the whole study.
Can you say something about the connection to analysis?
Yes. At the very beginning, we defined the convergence of a graph sequence. Now, if you work with convergence, then the first question is, what is the limit object? Now, we met that problem when you have the rational numbers, and somehow you have a completion of the set of rational numbers, and then this gives one way. So here, as always, we would have that possibility, that just to consider the completion of the whole thing. But it wouldn't help to answer many, many questions. And the first thing what Lovas and Szegedi, Balázs Szegedi did, they really found a very good object what to consider as a limit of a graph sequence. And the simplest way to formulate it, or the simplest object, is just a measurable function in 0, 1 square. One should consider more general spaces, so it is not necessary to stay with 0, 1 square, which turned out to be an extremely good model.
This limit concept, you mentioned that it has connections to many subjects, including physics. It also has some connection to the theory of computing. Can you say just 2 words about it?
Yes, that's true. Our idea is testing, mainly property testing. What we did, it was so-called parameter testing.